Hi class, and I'm gonna use this video tutorial to talk about tutorial number 9 because it remembers day. Okay, so in this video tutorial, we are going to talk about the new concept, engineering concept first. The concept is called harmonic motion. Okay, so harmonic motion is a new concept. As probably you haven't heard it before, but where it comes from is actually nothing new. Is what we have covered in the class, and we have done that in assignments. So definition. Okay. So what is called harmonic motion? If we have a particle, okay, so the particle is said, okay, to execute harmonic motion, okay, if its equation motion satisfies the differential equation. So satisfies a differential equation of the form. What kind of form is this? There, right? So if the particle's equation motion satisfy this format here. So what kind of format is this? This is nothing new here. This is actually just a homogeneous second order differential equation with the constant coefficients here, right? Now this omega naught in here, okay, has a special meaning. So this omega naught is a positive constant. Okay, it's a positive constant. This is basically going to be representing the frequency of the harmonic motion. Okay, x of t here, of course, is what describes the motion of the system, or it's basically the position, okay, of the particle. Okay. Now, essentially, when you look at this one here, now the object is what will be the solution of this one. Right, the solution of it will give you a function of x, and that function of x describes the harmonic motion of that particle there. Right. Now we have done many exercises on this because it's a second order homogeneous ODE. So the characteristic equation is lambda squared plus omega 0 to the power 2. Okay, so you have two complex roots. Okay, so apparently the solution for the motion of the particle is in terms of this equation here. Okay. So A cosine omega t plus D sine omega t. Now, because they all have the same frequency right here, okay, so two sinusoidal signal plus add them together, and you end up with another sinusoidal signal, basically. Okay, so as you have done in the assignments, the simplified version of this expression here is this. Okay, yeah, and the phi angle here is equal to tan inverse and b over a. Okay, yeah. And how do you determine the phi angle? And generally, you need to look at the actual location, okay, of a value, okay, and then you look at the actual value of phi. Okay. So this is basically a so-called harmonic motion. Okay, yeah, harmonic motion here. And sometimes we call it a simple, okay, harmonic motion. Because it's so simple, right? It just gives you sinusoidal signal here. Okay, yeah. Okay, so that's basically the definition here. When you in many situations here, when you have a system response which takes the form of this, okay, that means the system exhibits a harmonic motion. Okay, now, so where do we see harmonic motion? Okay, so this is a very important concept in mechanical vibration. Okay, when you learn vibration, you probably will come across this concept again. So where do we see of harmonic motion? One simple example, actually, we have seen that is a single pendulum problem. Okay. So let's see, I have a single pendulum here. Okay, it's a simple pendulum, okay, with point mass attached at the end of the string. Okay, in tutorial number 5, if you recall that. Okay, in tutorial number 5, we derived the equation for motion for this system. Okay, so if you remember that, so let's say if the theta angle between the string and the vertical line here, suppose that the length of the string is L. Okay, and apparently we will see the pendulum, you know, swing back and forth like this. Okay, assuming there's no friction. Okay, so here's your mass, okay, because of gravity. Okay, and if you remember that the equation for motion derived for this one here is, okay, theta double dot plus g over L theta equal to 0. Okay, sorry, and actually, yeah, in that case it's actually sine theta, okay, equal to 0. Okay, this is a precise equation motion. Now when theta is small, okay, so if you let it go, start from a very small angle theta, so when theta is small, okay, and sine theta is approximately the same as theta, so this equation is reduced to, okay, to this, okay, to this. Now if you look at this equation, that's a nonlinear equation, right? This is a nonlinear equation. But when you have a small theta angle and you have a linear differential equation now, okay, it's a second order linear differential equation. Okay. Now if I compare this equation, okay, with what I've given over here, and that's exactly the same kind of format we're talking about. So the theta over there is x, and the g over L over there is omega naught squared. Okay, yeah, right. So in this case, basically, we can let omega naught equal to square root, okay, g over L. Okay, so that's the frequency, and this is also called natural frequency of the system. Okay, yeah. So the solution for this second order system here is, and square root a plus b squared cosine omega naught t and minus phi. Okay, yeah. Okay, let's study this pendulum here just a little bit here, and just see if we can have some direct meaning or feeling of this physical system. Okay, so this theta here is angular position, right? It's a position signal basically. Now if I take a derivative of the theta, and I'll get angular velocity. Okay, so angular velocity, we call that omega, and d theta over dt, right? That's angular velocity. Okay, if I take a derivative, this one is very simple, and if negative omega naught square root a squared plus b squared and sine omega naught t minus phi, right? So that's angular velocity there. Okay, angular velocity. Okay, yeah. Now suppose we have some initial condition here. Okay, so suppose our initial value here, you have, let's see, theta of 0 equal to 1 over 10 reading. Okay, and the initial velocity is 0. Okay, yeah, and just see that L may be equal to 5 meter. Okay, gravity constant, of course, is 9.81 meter per second square. Okay, okay, so with these given conditions here, I'm able to get omega naught equal to g over L. You do the calculation, you get 1.4 reading per second. Okay, yeah, so that's your natural frequency of the swing of this pendulum. Okay, with this initial condition, I'll be able to calculate this A and a B. Okay, so just substitute initial condition into theta and theta prime. Okay, so we'll be able to get A equal to 1/10 and B equal to 0. Okay, so that means this phi angle and here is basically 0 degree. Okay, yeah. So then overall the theta, the motion of the system is 1/10 cosine 1.4t. There, so that's the position of this harmonic motion here. Okay, yeah. So now the next question here is going to be a very similar question to one of the Simon question in Simon number 8. Okay, so the question here I'm going to ask is, what is the velocity of the pendulum as it crosses the equilibrium position? Okay, so let's say your pendulum starts at this location, which is your initial angle. Let's say 1/10 reading, and then you let it go, right? So it'll swing to the initial to the equilibrium position. The equilibrium position is, this is your equilibrium position, right? Why is this called equilibrium position? Is because if you do have a damping, right, and the ball or the pendulum eventually will stop at here, right? It will become static here. So this is equilibrium position. So it'll go across this equilibrium position, and then it'll swing back over here. So basically, you're looking at here is, you're looking at two velocities, one going this way, the other going this way here. Okay, so the question is, what's the velocity of the pendulum as it crosses this equilibrium position or the central position? Okay, and of course, you can imagine that the magnitude of the two velocities are the same. It's just direction are not the same. Okay, at the equilibrium position. Okay, so what is the velocity of the pendulum? Okay, as it crosses the equilibrium position. Okay, and we're gonna talk about that based on the solution over here. Okay, with this equation here. Okay, so this is your harmonic motion equation motion here. Okay, and we're talking about velocity actually, so you need to take a derivative of this one here. Okay, so angular velocity. Yeah, so you got to be careful here. This velocity here is not angular velocity. This is actually asking you what's the linear velocity of the pendulum as it crosses this equilibrium position. Okay, linear velocity and angular position are not the same, so we'll see that. Okay, so angular velocity equal to d theta over dt. Okay, yeah, and we'll see what the linear velocity is. Okay, yeah, and based on this equation here, we get negative 1/10 1.4 sine 1.4t. Okay, yeah, so do a little bit simplification here to negative 1.4 sine 1.4t. There, because that's angular velocity. Okay, yeah. At the equilibrium position, okay, at equilibrium position, basically you see that equal to 0. Okay, you'll see that equal to 0. Okay, theta equal to 0 means at what time t that you will have this theta equals 0, because your start angle theta is 1/10 readings. Okay, yeah. So what does that mean is that gives us 1/10, okay, cosine 1.4 t, okay, equal to 0. Okay, or simply just cosine 1.4 t equal to 0. Okay, so this equal to 0, which means 1.4t equal to pi over 2, right? Well, not just pi over 2, because your swing is back and forth, you know, it's infinite terms. Okay, so first swing is pi over 2, and the second swing is u plus 2 pi. So you can have as many swings as possible, plus 2k pi. Okay, so well, not just pi over 2. Your 1.4t could also be 3 pi over 2, right? So well, let's take a look at this one here. It's basically a swing here and then back, right? And for the t value, right? So when it goes there, it's pi over 2. When it comes back, it's 3 pi over 2. Okay. So similarly, you also need plus 2k pi over there. Okay. So that's two possible solutions for the t here. But you know what? We actually don't really need the actual value for the t. Okay, don't really need that, because we are looking for the linear velocity or translational velocity. So which means, you know, when theta equals 0 and this equal to 0, and that's your value for 1.4t. Okay, now what does this mean is your sine, okay, 1.4t. Okay, yeah, instead of a 0, right, at this value, okay, it's 1. At this value, it's negative 1. So it's going to be plus minus what? Sine 1.4t. Okay? Yeah. Now why this matters? Because see, we're looking for the angle, we're looking for translational velocity. Now I'm going to derive an equation here, show you what's the relationship between translational velocity and angular velocity. But I can calculate the angular velocity, okay, at the equilibrium position, because omega angular velocity equal to negative 0.14 sine 1.4t, right? So that's why your angular velocity here, okay, omega, okay, equal to, okay, 1.4 sine 1.4t, okay, equal to, okay, negative positive 1.4, 0.4, okay, at equilibrium. At equilibrium. Okay, so now it's time to talk about this translational velocity or linear velocity. At equilibrium. Okay, well, your L, okay, remember the length of the string is 5 meters, okay? Yeah. So what's the linear velocity? Okay, so when you swing a theta angle, okay, your total the total displacement is L multiplied by theta, right? Yeah. So total displacement is theta. Okay. Now the translational velocity or linear velocity v, okay, is equal to ds over dt. Okay, so here L is a constant, so that becomes L d theta over dt. Okay? Or in other words, v equal to L omega. Okay? So this is what we're looking for. We're looking for the v, okay, at equilibrium position. Okay? So at equilibrium position, your angular velocity is this value. Okay, so your v, okay, will simply just 5, okay, multiplied by this value at here, okay, which gives you this one. So why do we have a negative value and positive? That basically refers to the angular velocity, the linear velocity back and forth. Okay, right? Yeah. So the plus sign is generally, so if I redraw it here, this is your m. Okay. Yeah. So the plus sign is normally used when the mass here, the pendulum is moving counterclockwise. Okay, and minus sign is when it's moving clockwise. So when it's going this way, it's a negative value. When it's going this way, it's a positive value. Okay, so counterclockwise. Generally, counterclockwise we think of it as a positive angle or positive velocity. Okay, and the counterclockwise, which is this is clockwise here. Clockwise is think of the negative value here. Okay, yeah. So that's how you get linear velocity or translational velocity for this kind of a rotational motion. Okay. This will help you in terms of this, one of the assignments for assignment number 8. Okay. So take a look at this tutorial here. Okay. Yeah. Okay. So let's take a look at the second example. Yeah. The second example here is basically we're going to solve for both based on what we have learned, solving non-homogeneous second-order ODE using method of undetermined coefficients. Okay. So this is also going to be the same method we're going to apply to example number 3. So method of undetermined coefficient. Okay. You need to look at the lecture notes. There's one page. Okay. In that one, many times you need to look at that as guideline for basic rules, modification rules, okay, right, and or some rules if necessary. Okay, so let's try to solve this one here. So we're going to solve y double prime minus 2y prime plus y equal to t plus e to the power of t. Okay. Okay, so you look at this one here. That's a non-homogeneous apparently. The forcing function here is your f of t. Okay, happen to have two kind of a different format here, right? Now one is the ramp type, and the other is exponential type. Okay? So if you recall that according to the basic group, according to that table we're given, so I think we're going to have to use is first we have to use sum rule, okay? Because you have two different type of forcing function here. Okay, yeah. But irregardless anything, the first step is always trying to obtain the homogeneous solution. Okay, and in order to get that, you come up with basically the characteristic equation. Okay, so solution for this one is fairly simple. If you don't remember the formula, you can simply simplify this one here. Okay, yeah. So that means lambda equal to 1. Okay. So what that means is you have a repeated roots at here. Right? You have repeated roots. So then our two basis solution, one is e to the power of t, okay, and the other one is t e to the power of t. Okay. So in other words, your yh equals c1 e to the power of t and c2t e to the power of t. Okay, so that's YH. Okay, now step 2, it's time to look for the particular solution. Okay, particular solution here. Okay, so when I'm looking for particular solution here, this is where I need to follow my tables. Okay, to pick up. First step is to pick up have a lucky guess of what kind of form for the YP is. Right? Yeah. Now, because I have two different types here, so I guess the first step I need to take two lucky guesses. Okay, so my first lucky guess, okay, YP1 corresponds to the t. Okay, according to my table, is K1t plus K0. Okay, yeah, correspond to this t here. And my second lucky guess, corresponding to this e of t, is going to be c. Let's see, e to the power of t. Okay, so that's my first guess. Yeah. So this is your initial guess here, initial lucky guess, right? The second step is always ask yourself, do I need to apply modification rule, right, for the initial guess? Well, you look at your lucky guess for YP1, and it doesn't duplicate any one of this solution in here, right? However, when you look at YP2, and that duplicates the one of the homogeneous solution at here. Okay, yeah. So essentially, what you need to do is, right, you need to multiply this one by t. Okay, so then you see, okay, I need yp2, right? Change that to ct et. Okay, well, hold on a second. You may think that's enough, but actually not, because why you examine again? Look at this one here, right? Because it duplicated also this one here now, and the only reason is because your lambda here is a double roots. Okay, so second chain modification, your yp2, right, should multiply t squared. Okay, so t squared here. Now this time this yp2 here doesn't duplicate any one of this one out, because this one yp2 that you picked is linear independent of any one of this one solution, homogeneous solution you get here. Okay, so now this and not this and this. Okay, because of the modification rule. Okay, yeah. Okay, now I have yp1 and yp2, and let's see, yp is yp1 plus yp2. Okay. Right. Alright, so now let's try to solve next object. What's the key 1, what's key not, and t? What's the c? Okay, because your particular solution, they are gonna be a certain possible values there. Okay. Okay, so what do? I take the derivative of yp. Okay, so let's see what's that become. So k1, and this one here, you need to apply the product rule. Okay, so 2ct et plus ct squared et. There, so that's yp prime. And then let's take another derivative of this one here, and this is gone, and product rule of this one, so 2c et plus 2ct et. Yeah, and plus 2ct et plus ct squared et. Okay. Okay, so now I have my yp prime, yp double prime, and maybe we can simplify this one over here. You can take the c out, and there are 2 et at here, and plus 4t et plus t squared et. Okay, so let's substitute this back into our original differential equation. Okay, so now your yp double prime minus 2yp prime minus yp, okay, equal to, okay, there's a fairly long expression here, so let's gotta be careful. Okay, equal to this, so that's yp double prime here. Okay, so that's yp double prime, and 2yp prime to 2yp prime over here. Okay, and minus the plus yp, and yp is over here, right? Yeah. So k1 t k naught ct squared et. Okay. Yeah, be extra careful what you write. Okay, don't write anything wrong. Don't make any unnecessary mistakes. All right. So, and we can simplify this whole expression a little bit, and then you will be able to get this if you are careful enough here. Okay, you get this right here. Okay. This term, right, equal to this term equal to your original differential equation, which is what? Which is t plus e to the power of t. Okay, so this term equal to this. Okay. Now I want this term equal to this, and then how do I get this term equal? So basically, what you need to do is you need to compare coefficients at here. Okay, coefficients. So this side is like t plus 0 plus e to the power of t. So then what would you do is you would just have to come up with 3 equations here. So this k1 equal to the coefficient of t over there, and the k naught minus 2k1 equal to this one here, and the 2c here, okay, equal to the coefficient here, which is 1. Okay, so That's a very simple linear equation. So k1 equal to 1, and k0 equal to 2, and c equal to 1 over 2. There. So that's the solution. Okay. So apparently your yp is t plus 2 plus 1 over 2 t squared et. Okay. And overall the general solution, okay, so the general solution is y equal to yp plus yh. Okay, yeah. So that equal to, right, just add all the two terms together. C1 et C2t et. Okay, so there. So that's the general solution here. Okay, yeah. So from this question, I think one of the things that you got to be careful is the modification rule, right? Modification rule. Okay, so let's look at the second example here. Third example, sorry. So for the third example, I'm going to ask you to solve is this one here. Okay. Y double prime plus y equal to sine t cube. Okay. All right. So this sine t cube here seems to be pretty scary, actually. Okay. So let's take a look at step number 1, of course. What's yh? Okay. Yeah. So this is yh is the solution of this. Okay. So lambda squared plus 1 equal to 0. That's characteristic equation. Lambda equal to positive minus g. Okay. So your yh, okay, equals to c1 sine t plus c2 cosine t. There, right? Yeah. Step number 2. Yeah, step number 2 is to obtain the yp. Okay. All right. So yp, you have to make initial guess for yp based on the forcing function sine t cube. Well, but if you look at our table there, there's no forcing function that takes the form of sine t cube of this kind of format, right? Okay. But as a matter of fact, if you remember in assignment number 6, okay, the bonus question, I'm not sure if you did the bonus question, is ask you to simplify that, okay, sine t cube into a sort of function of sine t, you know, or 2t, 3t, you know, kind of thing like that, right? Okay, so I want you to take a look at the lecture, the tutorial notes. Okay, I'm not gonna derive it here anymore. Okay, but basically sine t cube, is equal to this. Okay, is equal to this. Okay, so it's actually basically two sine function, add them together there. Okay, yeah. So what happens is this basically your forcing function has two sine functions here with a different frequency. Okay, so I guess we're gonna have to use that sum rule again, right? Yeah. So what we can do is we can see, okay, so let's see for this forcing function, right? And my initial guess yp1 for this one here, okay, is gonna be this. Okay, and for this function here, right? So that's correspond to this. And for this one here, okay, we're gonna have similar things. Okay, but we're not gonna use AB anymore, so we're gonna use c sine t plus d cosine t, you know, like this. Okay, yeah. Okay, so that's your initial lucky guess, right? Again, you had to ask yourself, do I need to apply the modification rule to either yp1 or yp2 or not? Okay, so let's see, yp1 here, right here, and or the forcing function here, it doesn't really duplicate any one of the solution over here. Okay, yeah. Now, however, this one here, right? The YP2, look at that, right? It's exactly the same format, okay, as the YH. It does duplicate, okay? So in this case here, this is no good, okay? So we need to apply modification rule. Okay? So then YP2, okay, cross it out, okay, multiply by T. Yeah. Okay, something here. There. Okay. So that's YP2. That's what we need to take. Okay. So overall, okay, your YP equal to A sine 3t plus B cosine 3t ct sine t and dt cosine t. Okay, so this is a very long expression for YP here. Okay, for YP. Okay. All right. We need to solve for A, B, C, D. Okay. So how do I solve that? Okay, extra patience is required. Okay. So calculate YP prime and YP double prime. Okay. So okay, let's calculate YP prime here. 3A cosine 3t minus 3B sine 3t plus, okay, well, plus what is your product rule now? We have product rule for this one here. Okay. In a second here, what I'm doing here, ct. Oh yeah. So ct cosine t, ct cosine t plus c sine t. Okay, and dt sine t. Oh, I guess we need to negative here. Okay, plus d cosine t. Okay, right. It's very long. Okay, and YP double prime. Okay, again. Okay, so now you have to quite a bit of patience is required here. But anyway, if you be careful here, and you'll get this. Okay. Yeah. Yeah. So seriously, you need to carry this out. Okay. Test your patience. Okay. See if you can get this. Okay. Write clearly and use as many spaces as you can. Okay, don't crowd everything into one little corner. Okay, so we got YP prime, YP double prime. Okay, let's double check everything's good. Okay, and we can substitute this one, okay, into here. It should satisfy this equation here, right? It should satisfy this equation. Okay. Okay, so let's see. If I substitute YP prime here, YP over here, okay, and do a little simplification, we can get this one here. Okay. So in the final exam, you'll have plenty of time, and one of the such kind of a test that I do is I test your patience. Okay, so that's your left side here. Okay, so your right side, okay, is this. Okay, so what do? I'm gonna have to compare coefficients, right, in order to solve that. Okay, so sine 3t coefficient is -4 and -1/4, so that means -AA equal to this. And we don't have any cosine 3t there, so that means -AB equal to 0. Okay, and cosine t, we don't have any coefficients there, so 2c equal to 0, and -2d equal to 3/4. Okay, 3/4. So what does that give us? A equal to 1/32, and B is 0. C is 0, and D is negative 3 over 8. Okay, yeah. So now we have A, B, C, D, and our general solution, okay, can be easily write down here. Okay, yeah. Okay, so that's basically the general approach, or what this tutorial is all about. Talking about solving second order non-homogeneous ODE using method of undetermined coefficients. The assignment number 8 also has some questions on using variation parameters. This tutorial doesn't cover that, but the next week's tutorial does. Your assignment due date is next Friday, so next week for November 18th. So you have plenty of time there. In the meantime, you can also take a look at the lecture notes in terms of the undetermined, in terms of the variation parameter methods. Okay, yeah. So anyway, if you have any questions, let me know. Okay, and we can definitely work on that. Okay, thank you.